This is Gianpaolo and I'll be doing part C of question 3. So part C states to use a midpoint Riemann sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1 over 6 times the integral of 0 to 6 of the function c dt. Using correct units, explain the meaning of 1 over 6 the integral of 0 to 6 the function c dt in the context of the problem. So we're going to first find the approximate value of this integral. So we're going to write down the integral, and since it's an approximate, we're going to do the squiggly line equal sign, which means approximated to. And to find our midpoint Riemann sum, we'll basically be adding the areas of these subintervals. So since these are areas, we're going to be multiplying base times height for an interval, base being the distance between the two x values and height being what the y point is at that certain x value is. So since we're not using x values, we're using t minutes, so instead of x it's going to be t, and instead of y it's going to be c of t. So we'll just convert it to that. So we know that they're all equal subintervals. We'll go ahead and put down 1 over 6 right here since we're multiplying it by the whole integral anyways. And then we'll put brackets and then put a parentheses. So we know that the subintervals are equal lengths. So there's 6 t points. So if we divide this into 3 equal lengths, then that means that each subinterval will have the width of 2, because we'll basically be dividing 6 by 3 and we'll get 2. So we can go ahead and input that in here, and we're adding this all together. We're adding all our areas together of each subinterval. So we have our bases down. Now we just need our heights. So to get our heights, since it's asking for the midpoint Riemann sum, we'll be getting the midpoint of between each subinterval. So the first subinterval is going to be from t equals 0 to t equals 2, and we'll go in between that and get a midpoint at t equals 1, and we're going to get our c of t value for that, which is going to be our height. So the c of t value for t equals 1 is 5.3. So that's our height for our first subinterval. And then we're basically going to repeat this. So for our next subinterval, it's going to be 11.2 at the t point of 2, or t equals 2, or t equals 3, my bad. And then we'll do the same thing at t equals 5. The height is 13.8. Okay, so now that we have that down, we can just go ahead and simplify this. So we'll do this multiplication first. 10.6 plus 22.4 plus 27.6, and we add these together. Do some scratch work on the side. So you get 33 plus 27.6. You get 60.6. So let's erase the scratch work. And then 1/6 times 60.6 is going to be 10.1. And that is our approximate value for the integral. And then the second part of this question is asking, using correct units, our units, yeah. So we need to add our units to here. So the initial question gives the units in ounces. It says right here, selected values of c of t measured in ounces are given in the table above, so we're going to use ounces. And then moving on to the next part, it says explain the meaning of the integral in the context of the problem. So we're basically calculating the area and then multiplying it by 1 over 6. And that's actually the formula for average values. And so basically, because we're multiplying it by 1 over 6, and there's 6 points on there, we're taking the average of the area of the entire amount of coffee in the integral. If it was just the integral itself, would just be taking the total amount of coffee in that time frame of t equals 0 to t equals 6, but since we're multiplying it by 1 over 6, we're getting the average of that. So the integral 1 over 6 from, 1 over 6 times the integral of 0 to 6 ct dt means that it is the average amount of coffee in the time of 0 to 6 minutes. Or I could just rename amount to average ounces just to be more specific. And that is our final answer for part C.
Okay, so for this question asks us to consider the differential equation dy over dx equals y squared times the quantity of 2x plus 2, and it tells us to let y equals f of x be the particular solution to the differential equation with initial conditions set at f of 0 equals negative 1, and it tells us to find the limit of f of x plus 1 over sine of x as x approaches 0, and it tells us to show our work. So what we can do right now is so if we find the limit, of the numerator using direct substitution, we would find that since the initial condition is f of 0 equals negative 1, if we use direct substitution, we would find that the limit equals 0. And then if we move on to the denominator, the limit of sine of x as x approaches 0, using direct substitution, you would find that it's also 0. And because both the numerator and denominator are 0, that's an indeterminate form, which means that we can use L'Hopital's rule to further evaluate this problem. And L'Hopital's rule basically states that if a limit produces an indeterminate form, which is 0 over 0 or infinity over infinity, then you can differentiate both the numerator and denominator to further evaluate that limit. Just writing it all out for you here. So it would be f prime of x over g prime of x. So yeah, and so if we apply this rule to this limit equation we have right here, we can differentiate this top function, this numerator, so it would be the limit of f prime of x as x approaches 0, and because of the way this problem is set up, we know that dy over dx is actually equal to f prime of x, so we can write that out. 2 over dx equals y squared times the quantity of 2x plus 2, and then since it gives us this initial condition, we can actually plug those values in for y and x. So dy over dx equals, we're plugging negative 1 in for y, and then we're plugging in 0 for x. And if we just evaluate this, it's going to be 1 times 0 plus 2 times the quantity of 0 plus 2. That's 1 times 2. So we would finally get that dy over dx equals 2, which means that the limit of f prime of x as x approaches 0 equals 2. So that's just the limit of the numerator after we differentiated it. And then if we differentiate the denominator, which is sine of x, the derivative of sine of x is actually cosine of x. So we're going to write the limit of cosine x as x approaches 0. And if we directly substitute that to solve the limit, then we would get 1. So that's the limit of the denominator after we differentiated it. So our final answer, after evaluating everything, the limit of f of x plus 1 over sine of x as x approaches 0 is equal to, due to L'Hopital's rule, the limit of f prime of x over cosine x as x approaches 0, and then we got 2 over 1, and then so that would make our final answer 2 for the limit of f of x plus 1 over sine of x as x approaches 0. Yes.
So the question for 5b was, use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of 1/2. And it gives us that dy over the derivative of y with respect to x is y squared times 2x plus 2. And it also gives us that y equals f of x. And it also gives us that f of 0 equals -1. So the first thing to do is to identify Euler's method, which is just f of x plus the change of x equals f of x plus f prime of x times the change in x. And then you would plug the numbers in. So it gives us that x is 0. That's what we want to start with. So f of 0 plus the change in x, and it tells us that to approximate f of 1/2 with 2 equal steps starting at 0, you would use 1/4 because that's just 2 equal steps, and that's half of 1/2. And then you would plug in the other numbers. So f of 0 plus f prime of 0 times the change in x, which is just 1/4. And then you would solve it. It tells us that f of 0 is -1. And then f prime of 0, you would plug 0 into this equation right here. And it tells us that y is just f of x. And f of x at this point is f of 1 is just 1/4. So you would do 1/4 squared times 2 of 0 plus 2. And times 1/4. After you solve this, you get -1 plus 2 times 1/4. And this is just -1 plus 2 over 4, which equals -2 over 4. And this is f of 1/4. So the next thing to do is to solve for f of 1/2. So f of 1/2 equals f of 1/4, because that's what x is at this point, because you solved before. So f of 1/4 plus f prime of 1/4 times 1/4, because the change is still 1/4. And f of 1/4, we solved it right here. It's negative 2/4, or just -1/2. So -1/2 plus f prime of 1/4. You would plug that back into this equation right here. And y, once again, is f of x. And f of x at this point is half. So it would be 1/2 squared times 2. And x is 1/4 plus 2. And then you would solve, and then also times 1/4. So then the next thing to do is to just solve these solve the parentheses and all the numbers and algebra stuff. So 2 times 1 over 4 plus 2 gets you 5 over 2. That's 5. And then 1 over 1/2 squared is just 1/4. And then negative 1, you just bring that down, times 1/4. So then you can multiply these. So 1/4 times 5 over 2 is 5 over 8. 5 over 8 times 1 over 4 is 5 over 32, plus negative 1/2. Negative 1/2, to get common denominators, is becomes negative 16 over 32, because that's the same thing, plus 5 over 32. Sorry. Negative 16 over 32 plus 5 over 32, which equals negative 11 over 32, which is what f of 1/2 is. And that is how you use Euler's method starting at x equals 0 to approximate f of 1/2.